Namaste, my students and other viewers, respected viewers. Now I discuss on unique factorization domain. So here is the definition. What's unique factorization domain? It first will be a integral domain, and then every element of this domain becomes a factor into finite number of irreducible elements up to and also uniquely. So here is the definition: an integral domain D is said to be unique factorization domain UFD if the following conditions are satisfied. Number one, every non-zero and non-unit element in D can be expressed as the product of finite number of irreducible elements. If P1 into P2 into Pm, into means the composition of the integral domain, multiplication, composition, and Q1, Q2, Qn are two factorization of the same element of D, then M equal to N and Pi, Qi are associates for some Ij, that is the decomposition is unique up to the order and associates of the irreducibles. Here is example. All we know in number theory that every element of every integer can be expressed as a finite product of primes or power of primes uniquely, except just the order of the primes. So here Z is UFD because every element of Z except plus minus 1 can be expressed as the product of finite number of primes, uniquely except the order of the factors. Here we write prime because irreducible elements we can if we write it is prime, then it is surely irreducible because in integral domain every primes are irreducible. So therefore here we can write as primes are irreducible, so the definition of integral unique factorization domain can be applied for Z also. Now we have already know that in integral domain every prime element is irreducible, and in PID both are identical. Similar result hold if we replace the PID by UFD. So in a UFD, irreducible elements are prime element. That is a theorem, we have to prove it. So for the proof, consider an irreducible element P in UFD and consider P divides A into B. So we have to show that either P divides A or P divides B. So now P divides AB implies there exists some C belonging to D such that PC equal to AB. As P is non-zero and non-unit, because of the definition of irreducible element, we have to mention that a non-zero non-unit element for its definition. If P is non-zero and non-unit, so not both A, B are units. If both are units, then P cannot be irreducible because then P becomes unit. So that's why at least one of them must be non-unit. So now if A, say B is non-unit here, case 1, B is non-unit. So then B can be written as P C A inverse because PC equal to AB. So P divides then B. If A is non-unit, then we can similarly show that P divides A. Now, if both AB are non-unit, then D is UFD, set D is UFD, then every element A and B can be expressed as A equal to P1 multiplication P2 multiplication Pm, B equal to Q1 multiplication Q2 dot Qn, where P1 P2 dot Pm and Q1 Q2 etc. Qn are irreducibles by definition. So if C is unit, now another case, if C is unit or C may not be unit. If C is unit, then from AB equal to PC, what we write? See that P is irreducible. So C is unit, P is irreducible. Therefore, PC is irreducible. You know, associates of a irreducible element is irreducible. So PC is an associate of P. Therefore, it is irreducible. And so A into B is irreducible, which is a contradiction because A has factors by P's and B has factors by Q's. Therefore, C cannot be unit. Now, C as belonging to unique factorization domain D, so C can be expressed as T1, T2, Tk, where T1, T2, Tk are irreducibles in D. Okay. Now, what we are writing from PC equal to AB? That PC, I just put the value of A and B here. That means P1 up to Pm multiplication by Q multiplied by Q1 give to Qn, and here P is and what is C is T1, T2, Tk. So this is an expression for PC equal to AB. Now D is U of D. So P must be an associate of one of Pi and Qj. Why? Because in unique factorization domain, this expression and this expression are same. That means these two represent the same element. So whatever may be E, A, B, P, C. But as these two factorization are equal, so in D, as D is unique factorization domain, so one element of here is associates of the other here. So P may be associates of P, some P's or some Q's, like this. So if P associates of Pi, say Pi, and Pi is a factor of P1 up to Pm, that means A, so therefore P divides A. Similarly, if P is associate of Qi and Qi divides Q1 up to Qn, that is B, so therefore P divides B. Consequently, P divides AB implies P divides A or P divides B, and therefore P is prime in D. Corollary, as U of D, so prime element and irreducible elements are equivalent. Actually, there is no distinction between prime element and irreducible element in unique factorization domain. Okay, because in integral domain, you know, prime elements are irreducible, but here we see that irreducible elements are prime. So therefore, combining these two, we get this corollary. Now, as you see in PID, irreducible elements are prime elements and reverse also true. In UFD, we have just seen Prime element, there is no distinction between prime element and irreducible elements. So it's very pertinent to think of a relation between PID and UFD. So here is a theorem. Every principal ideal domain is a unique factorization domain. Every PID is an UFD. So for this, we recall two requisites to lemma here, which we have already proved in the chapter PID. Here, these two lemmas are: in PID, if UI sequence is a strictly increasing chain of ideals, that is UI is a subset of UI plus 1, or I belonging to N, so then this chain is of finite length. That means after certain stage, all UIs are same. Next lemma, in a PID, for every non-zero non-unit element, there exists an irreducible element P such that P divides A. We have proved it in principal ideal domain. I am just stating these two lemma for our uses. So now I am going to the proof of the main theorem. So what is the theorem? Theorem is here: in principal ideal domains are unique factorization domain. So let it be a principal ideal domain. We have to show that it is unique factorization domain. So in order to prove it is unique factorization, we have to take an element, any element in PID, and ultimately I have to show that this has unique factorization. Let A be a non-zero element, non-unit element, of course, in the PID. Okay, so by lemma, there exists an irreducible element P1 such that P1 divides A. So that means A equal to P1 U1 for some A1 belonging to D. This means, what does it mean? This means A belonging to principal ideal generated by A1. That means principal ideal generated by A is a subset of principal ideal generated by A1. So there are two possibilities. Either principal ideal generated by A is a proper subset of principal ideal generated by A1, or equal. Suppose they are equal, then what will happen? If they are equal, then we already know in divisibility in an integral domain that A1 becomes AR for some unit R in D. You easily can prove it, but in this chapter, I am not to elaborate the proof of these results. But it's very simple, you can try it. Then A equal to, just I put the value of A1 equal to AR here, this way here. So I am just putting A equal to ARP1. That means just it can be written as A into 1 minus RP1. As D is an integral domain and A cannot be 0, you see here A non-zero elements. So therefore cannot be 0. Therefore RP1 equal to 1. That means again you see that R is unit. But from RP1 equal to 1, you just see that both R1 and R and P1 are unit. So clearly P1 is unit. So now see this here. P1 is unit. But you see here P1 is such that P1 divides A and P1 is irreducible. So P1 cannot be unit, cannot be non-zero. That means P1 P1 is unit, a contradiction, and it is because of this relationship. Therefore, this relation not hold. So what will hold? A, this strict, this principal ideal generated by A is a subset, proper subset of principal generated by A1. Okay, so now I'm writing this here. Now, if A1 is unit, next question, if A1 may be unit or not unit. If A1 is unit, then what will happen? P1 A1 is an associate of P1, and which gives this is irreducible. That means A is irreducible. Okay, A is irreducible, and so A has no factorization. So A has no factorization means A. So this theorem is obviously true because A is irreducible. So only one irreducible element express A. That means that itself. So so by default, it is true. Next, so A1 is not unit. So if A1 not unit, then there exists an irreducible element P2 such that P2 divides A, as by definition of so from the lemma 2 actually in it is in PID. So P2 divides A. That implies A1 equal to some A2 to P2. You can write it. Okay. So this implies just putting the value of A1 in A equal to P1 A1 relation. So therefore we get this result. So what we have seen from here that just okay. So here this one. So A belonging to here. That means I think it is. Just see here from here. A1 is A to P. That means A1 belonging to principal ideal generated by A2. That means principal ideal generated by A1 is a subset of principal ideal generated by A2. So we write it. So are these two, this equality cannot hold as you can see here also. So by the same type of argument, we just write here is a proper subset. A1 is proper subset of A2. That means principal ideal generated by A1 is a proper subset of A2. Okay. So if A2 is unit, again A2 is unit, then what will happen? That means A2 is unit means P2 and A2 is irreducible. That means A1 is irreducible. Okay. Then, so what will happen? So P1, P2, here you can see here. So if A2 is unit, then P1, P2, A2, P1, P2 is an associate of P1, P2. Again, P1, P2 actually has factorization, and P1, P2 again has no decomposition. So therefore, A has factorization P1, P2. That means A is associates of P1, P2. A is associates of P1, P2, and P1, P2 is the factorization of A. So if A2 is unit, then we see what I have to prove that. So from the definition of unique factorization domain, condition 2 is satisfied here. Condition 2. So now A2 is not unit. A2 unit. Again, you see that A equal to A2 P1 P2. What will imply that A2 is unit, so A2 has no factorization again, so therefore only factorization P1 P2, okay, which are irreducibles, So therefore A has factorization P1, P2. If A2 is not unit, then A2 can be written as A3 into P3. Or P3 is irreducible, and we can write from A2 equal to A3 into P3, this one, and similarly we have get in a chain of process in the same type of process. That means proceeding in this way, we get a chain of ideals like this. A principal ideal generated by J, proper subset of principal ideal generated by A1, and it is again proper subset of principal ideal generated by A2 and so on, which is if actually of finite length, which is of, this is one, this is which is of finite length, which is, so this one actually, this is of finite length by above lemma. Okay. So now then for some n, we can write A equal to P1, P2 dot Pn into An, where An is unit and P1, P2, Pn are irreducibles. So A is expressed as the product of irreducibles in this one. Now to so its uniqueness. So that type of decomposition is unique here. So for this, we consider any two type of expression of the same element. So A has a decomposition P1, P2, Pn, and A has another type of decomposition PQ1, K2M. I just take it. We have to show that these two decomposition are actually unique except the order of the primes and their associates. Okay, let An, you see here N, you see here M. So let N less than M. N less than M. So what will happen? Then we just rewrite this term in this P1 bracket in P2 up to Pn and here Q1 up to Pn. So what does it imply? Implies P1 divides Q1 up to Q1. And then it again implies that Q1 up to Qn, this multiplication is belonging to this principal ideal generated by P1. You have already known from the divisibility of an integral domain. But P1 is, what is it? P1, as P1 is irreducible, so therefore principal ideal generated by P1 is maximal. Again, you know it, maximal. And so maximal ideal is again prime ideal. Q1, Q2, Qm are all belonging to, product belonging to that, this principal ideal, this principal ideal. This principal ideal as well as this is prime ideal. So by definition of prime ideal, this Q1 up to Qm as belonging to this prime ideal, so one of them. So one of Q1 up to Qm is in this one, this ideal. Okay, prime ideal because P1 is prime ideal. So let say Qj just belonging to this prime ideal. Then Qj equal to, we can write what? Qj equal to some P1, some Pn, right? Qj equal to P1 into some U1, U1 belonging to D. Since P1, Qj are irreducible, P1 and Qj are all irreducible because here you see here this decomposition of irreducible elements. So P1, Qj are irreducible elements. So therefore only possibility is here U1 becomes unit. So then P1 into first bracket P1, P2 into the Pn, that is equal to Q1 up to Qj minus 1. Just put the value of here Qj from here, Qj from here. Just I put it here. So we get just after erasing this bracket and taking P1 outside, we have as integral domain also. Therefore, P2 up to Pn, that is equal to Q1, Q2 dot Q seed Qj minus 1, 1 Pu U1 is remaining by side, and then Qj plus 1 adds up to Qm. So it is because of the integral domain. Repeat this process now. We have up to P1 for this P1, P2, P3 up to Pn. So for each of them, we'll then replace each of Qi's, and after reducing Pi's for we have 1 equal to U1, U2, UN, Q1, Qn plus 1 up to dot dot Qn. You see here, n is less than m. So therefore, all Pn's are, you can see it is cancelled or like this because integral domain, so no zero divisors. So you just what types of you can get cancellation for. So one is here U1, each of for each of Q1, Q2, Qn, and so we get an U1, U2, Un, and ultimately the remaining Qs, which starts from Qn plus 1 to Qm, are here. So therefore, this 1 equal to Q1, Q2, Qn plus 1 dot dot Qm. And that means all of these are unit. All of these are unit in D. But you see, U1 up to Un, yes, of course, units. But we cannot say Q1 up to Qm are units because Q1, Q2, Qn plus 1 up to Qm, these are all irreducibles. So this relation cannot hold good, and it is only possible if Qn plus 1 up to Qm is absent. That means if n equal to m, that is n equal to m. So I cannot say here at once, I have to prove it again. So here, as these are units, we have a contradiction, therefore Qj is, okay, these are irreducible as. So therefore, we cannot say n less than m. We cannot say n less than m. So n less than, for n less than m, we have this type of contradiction. So what will happen? So then n greater equal to m may be hold. But again similarly, n lesser equal to m gives rise the same type of contradiction, and so from them we have we can say that m equal to n. M equal to n. So the definition of unique factorization of first, second definition, point 1 is clear. Also, P1 up to Pn and Q1 up to Qm are irreducible. So Pi is an associate of Qj, because here you see Pi, these two are same. That means one is associate of other. So Pi is associate of some Qj and vice versa, except the order of the factors. Consequently, D is an UFT. So and therefore every PID is UFD. But the converse is not true. Why? Why? It is the example of ZX, and it will discuss again in this chapter also, but later on. Converse may be true under certain condition. What that condition? If every proper prime ideal is maximal ideal, you know every maximal ideal is prime. But if every prime ideal becomes maximal, then UFD becomes PID. I just left it as an exercise, and this exercise is given in Galen. Now, for the time being, I am now discussing on this definition: content of a polynomial. Let fx an x to the power n, an minus 1 x to the power n dot 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 an all are in plus. Where a is at the are in UFD D, that means this polynomial over D. The common GCD of the coefficients A0 up to AN, we just denote it by CF, GCD of this. So it is sometimes called content of it, and it is I'm writing it here CF. Now a polynomial is called primitive polynomial if its content become unit, not unity also unit, but no unit. The content of the polynomial becomes unit. Also, GCD of any finite number of integers is not unique. In fact, GCD of any finite number of integers, it can be any finite number of members of an integral domain is not a unit, because if some D is GCD of some A1 up to N, then UD is again a GCD where you is an unit. So associate of a GCD is again GCD. So that's why a collection of members, finite number of members, has no unique GCD, but it is there are so many GCDs. So therefore, content of a polynomial, as it is GCD of the coefficient, and GCD are not unique. So therefore, content of a polynomial actually is not unique. If D equal to Z, then a polynomial fx belonging to zx, that means polynomial over the integers, is primitive if CF equal to, surely by definition it will be plus minus 1, because in Z unit elements are nothing but the plus minus 1, but some author use it as 1. So I am leaving it this type of differences. So I am going to take this definition: primitive, what is primitive, what is content. So now we have this lemma is very simple. A non-zero polynomial UFD can be expressed as the product of primitive polynomial over D and an element, unit element of D. You can see, just you can check it. Say suppose 2x square plus 4x plus 6. So here you see the GCD of 2, 4, 6 is 2, which is what I'm telling you now. This is actually, this 2 is not over Z. If we think of this, is not unit. But you can take it as in R, then you can think of. That means you just take common two element, then get 2 into x square plus 2x plus 3, that is where x square plus 2x plus 3 has contained is your uh, unit. So therefore it is primitive polynomial and an element of D, that is your 2. Here the Gauss lemma, product of primitive polynomials is again a primitive polynomial. So I am just considering finite number of elements. So my friends, you just see here, it is a problem here. This sometimes unit, but it is better to leave it because this may be unit, may not be element. So just you write it here, an element of D, an element of D. We just write it here. Okay. So here lemma, Gauss lemma. So what is it? The product of primitive polynomials is a primitive polynomial. So for this, let fx equal to this an element of here fx equal to summation I equal to 1 to n ai x to the power I, gx equal to summation I equal to 1 to n bx x to the power I be two primitive polynomials. Then what will say? Be two primitive polynomials. That means here cf equal to is an unit element and gf also an unit element. Not unity, but unit element. Unity may surely an unit, but in Z you can say unity, but there is some also one also minus one also there. So take it the definition as unit element. So then fx into gx, that is equal to summation I equal to 0 to m plus n ci x to the power I. If you write it this in form, then what will be ci? Ci means that means what is ci? Ci, it is called ck. So ck equal to summation I plus j equal to k, ai plus bj for 0 lesser equal to k, lesser equal to m plus n. Okay. Now, next. So this one, let d equal to HCF of C1 up to Cn plus n. So in order to prove that f into g is primitive, we have to show that this d becomes unit element. So if it is unit, then okay, clear. So but if d is not unit, then what will happen? We must have a contradiction according to the mood of this lemma. So for this, suppose d is not unit. If d is not unit, and you see in PID, so it is UFD. For every element, there exists an irreducible element. That means lemma 2. Every non-zero non-unit element, there exists an irreducible element P, such that P divides D. Here P divides D. P divides D. As P divides D, so these elements is HCF is D. That means P divides CK for all K belonging to K equal to 0 up to m plus n. Okay. So P divides Ck. Since Fx is primitive, therefore P cannot divide HC of A0, A1 up to An because this is unit. Fx is primitive means this is unit. So there cannot exist any irreducible element which divides this one. In particular, P cannot divide this one. So what will happen? Let T be the smallest element, smallest suffix such that this P does not divide T. Okay, HCF, P cannot divide HCF. Okay, so P cannot divide HCF means P cannot divide every A0 up to N. It is not true at all. Sum of at least one of them is not divisible by P. So I am taking a smallest element, smallest suffix such that P cannot divide 80, and after that P divides all of them. And we take S be the smallest suffix such that P does not divide BS for the G. Okay. So consider C T plus S. So that we just consider this element. What is this? This I plus J equal to T plus S AIBJ. So by our choice, P small, you see here, P here, let T be the smallest suffix such that 80. P does not divide 80. That means P divides before that. That means P divides A0, P divides A1, P divides 80 minus 1. So this yields as P divides up to 80 minus 1. So you can think of A0, A1, 80 minus 1. Each A0, A1, 80 minus R is a factor of P, and therefore these total things has factor P. That means P divides this total thing. But in C T plus S, the rest portion are after that. So what is it? Similarly, P divides A T plus 1, B S minus 1, and A T plus S B0. B0. Just from you. So okay, it is very simple. You just elaborate this structure and get this portion. Now from this elaborate form of this structure and from these two relations, what will you see? P divides ATPS. P divides ATPS because P divides here, P divides them, P divides CK. That means for all K. That means P divides C plus S. So here, this here, and this three, you get P divides ATBS, and so P divides either AT or BS, either AT or BS, because here P is prime. So which is a contradiction, because you see here P does not divide AT or BS, but we deduce it here, P divides AT or P divides BS. So a contradiction, therefore F into G. This contradiction due to this P divides if not unit. That means if D becomes not unit, we have this contradiction. Therefore, D becomes unit, and so fx gx are primitive. Okay. Now we prove it that d is a UFD, then dx is a UFD. So what we are now, so for this we take fx is a non-zero, non-unit polynomial in dx. Then we have to show that. F can be expressed b1 up to bs p1 dot p1x dot pmx, where bi's are irreducible in d and pi's are irreducible in dx. Okay. So let fx be a non-zero and non-unit polynomial in dx. Then we have to show that fx can be expressed as b1 up to bs p1x dot pmx and their multiplications, where bi's are irreducible in d and pi's are reducible in dx. If fx become b1 up to bs p1 dot pmx, and which is again has another expression c1 up to ct q1 up to dot q1x, where bi's and ci's are reducible in d and pi's and qi's are reducible in dx. Then we have to prove s equal to this t and m equal to this. And also bi and ci are associates and pi qi are also associates also. So for that, so fx be a non-zero non-unit polynomial in dx if degree of fx non-zero non-unit polynomial dx. Okay, if degree of fx equal to 0, then f is constant, and as d is UFD, so what will happen? Then the fx as a constant, so it has a unique factorization. So now a dfx greater than 0, b denote the content of f, and b equal to we can as b content of f x and b belonging to UFD, so b can be written in this form by the product of irreducibles in d. Okay. Then fx can be written as b1 up to bs into f1x, where f1x belonging to dx, no problem, and is a primitive of fx, you know it, a primitive of s, an element of d. I have studying a result previously here. So, and degree of fx becomes degree of f1x, very clear, as b1 up to bs. This is an element of d, so its degree becomes 0. Therefore, in order to equality of these two expression, we have degree of fx and degree of f1x becomes same. Now it is sufficient to show that the primitive polynomial, that fx of positive degree, can be written as the product of irreducible polynomial. Actually primitive polynomial of polynomial fx, no, this is actually fx, no, not fx, but it is actually f1x. A positive degree can be written as the product of irreducible polynomial of positive degree. Okay, can be written as the product of positive degree. And so for it, what will happen? So we prove it by induction on degree of fx. If degree of fx equal to 1, then what will happen? Then the fx is already irreducible and we are done. What is it? If degree of 1, degree of fx equal to 1, what will happen? That means here it is just a just AXB type of genus, and you know if it is degree F1, actually degree of Fx equal to 1, then if you write it can in some gx into hx, so one of the polynomial becomes of degree 0, and which is not possible because f is reducible then. So as f cannot be written as g into h, therefore f is irreducible. So therefore fx is already irreducible, and we are done. Now suppose that every primitive polynomial of degree less than, actually all are, actually this is all are f1 should be, all are this is also. So every primitive polynomial of degree less than degree of f1x can be written as the product of reducible polynomial of positive degree. So just if fx, again f1x is irreducible, then we have nothing to do. Otherwise fx can be written as, again also it is f1x, can be written as gx into hx, where gx into hx are primitive and have degree less than fx, and thus by induction both gx and hx can be written as a product of irreducible polynomial of positive degree. Clearly then fx is also such a product. So such a product by this one, by irreducible polynomials. So such a product, and therefore polynomial fx can be written in the form of the product of polynomials, primitive polynomials together with b1 up to bn, and the element coefficients of which are in d, actually not in dx. For uniqueness, that fx has two type of expression here, b1 up to bs, p1 up to pm, c1 up to ct, q1 up to q1, where b's and c's are a particular irreducible element of degree 0, and px, actually I am writing here in particular. That means B1 up to BS, Q1 up to C1 up to CT, these are all actually belonging to D, and so in particular it can be treated as an element of dx of degree 0. Px and Qx are reducible primitive polynomials of degree. Just I am writing these two type of expression of fx here. Now fx is a non-zero, here, so let b equal to b1 up to bs, c equal to c1 up to ct. I'm writing it here. Then px and qx are primitive. Here just p, these are all are primitives, and these are also primitives. So it follows from the Gauss lemma, this product of primitives is also primitive, and primitive polynomial is primitive. Here this is also primitive. Okay, hence both bc as it is primitive, so bc must be associate, and each is a content of, as it is primitive, so therefore this becomes a content, and also this becomes content of f, and is a GCD of f, so therefore this to be primitive becomes associate, so bc becomes associate of fx. Then from the definition of u of d and d, as these two are associates and it is expressible by irreducible elements, so therefore by the definition of u of d, s become t, and di become ci into some di for di belonging to d. Then from this relationship, that means we have seen here also. Then from these two relationship, after cancelling means it is as integral domain. Cancelling C's, we have, I just put the value of bi by di ci. Just replace bi by di ci. So here you get the di's here together with p1 up to pm, and here you just cancel it out, c1 up to ct as you see is equal to t. So therefore you write q1 up to qn. What will happen? So this implies in viewing, Px and Qx are elements of the corresponding field extension. Why? Because I have to think a divisibility. So therefore, I'm going to and field extension. So know that these results, you know that every integral domain is either a field can be extended to a field. So Px, Qx are elements of the corresponding field extension fx, and Px and Qx are irreducible. Irreducible means here we just state here the definition. So P1x divides Q1x. So P1x divides Q1x, and see here the coefficient of P1x here, coefficient of this here. So the ultimate resultant, if it is a polynomial, then coefficient becomes a rational form. A rational, it is better to say, not to say rational, but an extension of these into division like. So I am writing field extension. So I am writing it here, field extension. So P1 divides Qix for some I less than S. So Qixb, just put the Q1x, renumbering these. So if Qix becomes Q1x, then what will happen? Q1x become P1x into U1. U1. U1, what is it? U1 must be unit in D, as P1, Q1 are primitive. P1, Q1 are primitive. Because if it is not unit, then U1 into P1x cannot be primitive, and so Q1 not be. But which is not true. So then after cancelling P1x, both sides of this relationship, I'm just replacing this one. So we get D1 up to DS, P2 up to PM. Again, here is U1, Q1, Q2, dot Qm. So just continuing this process successively and considering m less than n. Then after m step, we get just you put one by one, replace one by one and cancel them. So you get here D1 up to DS and here U1 up to UM and rest portion Q1 up to Qm. You have just see the technique of the proof, you have already seen it. So this means LHS of this relation becomes a polynomial of 0 degree, but here this is a polynomial of 0 degree, but this is not. So ultimately, this is a polynomial of non-zero degree and this is a polynomial of 0 degree, and these two are equal, which is impossible. Therefore, m less than n, it is not true. It is not true. And similarly, we have same type of impossibility for m greater than 1. So ultimately, we conclude m equal to n. If m equal to n, then Pix equal to Uix for some unit I belonging to S. So therefore, Pix, Qx are irreducible, so they are associates in D. That means, what do we say? Here, so for uniqueness, So so for uniqueness, I am showing that S equal to T, M equal to N, Bi is associate of Ci, Pi is associate of Qi. Just see here, M equal to N and M equal to N, and Pi is associate of Qi. So Qi is unit. So associate of Qi. So therefore, we see all the conditions of the UFD is satisfied here, and so we can say that every UFD, if D is UFD, then dx is UFD. So if D is UFD, dx is, if D is UFD, then dx is UFD. That's all the proof here. And but here, so therefore, if Z is UFD, then Zx is also UFD. But here Z root minus 5 is not UFD. I have discussed it in my next lecture. So for this, it's a long video, almost more than 1 hour. Thank you very much for listening me. Thank you.